Hi, everyone. Thank you for coming to the workshop, the data workshop. So today we're going to have three speakers, and each of them will share their experience on how to deal with the data, especially data quality checking and inspection. We will start with Kyle, and then Ann, and then me. So let's go. And before that, I want to mention for the online participants, if you have any questions, welcome to type in the chat window and I will try to catch it. We will have a 5 minutes question and answer section at the end of each of the speakers. And so we were able to address your question at that time. Okay, then let's go. Go ahead.
Okay. Okay, let me switch over to R. Okay, so the data set that I'm going to go through is the kelp canopy biomass data set. So just kind of a really brief overview of the data set, how to download the data set, subset it for the data of interest out of it, subset it for a spatial area of interest, and then a quick example of how to plot that data to make sure that you actually subset the right area of interest. And then one example of how you can just do some like basic manipulation with the data to show some sort of like pattern or whatever your kind of variable of interest is in. So for anybody that's following along with mine, it's PC oriented, which is in reference to these first three lines. The package that I'm using just for some of this mapping stuff, this USA boundaries, seems like it might not work on Macs. But it's just the boundaries data set to get like state outlines and stuff. So you could easily find an alternative for that. And I'll look later and find an option to add in here. I just didn't know it didn't work on Macs until this morning. So the first few lines here. So let me talk about the data set first. The kelp canopy data set is one of our LTR long-term data sets. It is a Landsat derived data set. So starting in 1984 through present, we have kelp canopy data from every Landsat pass this is data sets for like the entire state of California, but so over the region, the data that we have online is aggregated quarterly. And the reason we do quarterly data is to help filter out noise with tide effects and other effects that might just add some variability into what the satellite's actually seeing. And it also helps us eliminate like cloudy days and other days where the data quality is poor. It is possible to get more frequent than quarterly, like monthly values, for example. It just requires a lot more data checking on your part if you're going to use monthly rather than quarterly. And then also somewhat still in progress is a kelp canopy data set using planet satellite imagery. So that would be a much shorter time series, like 2018 to present. But planet satellite imagery, when that's ready, would provide you a higher resolution data set. So the main difference between the two is the data we're going to look at today with the Landsat kelp canopy data is based on 30 meter pixel size in the satellite imagery. So what that means is every pixel in the image represents a 30 meter by 30 meter square of space on the ground or on the ocean surface. The planet data set would be 3 meter by 3 meter pixels. So it could be it's a lot higher resolution. And planet satellites are near daily passes. So as long as there's clear weather, we get a lot more data compared to Landsat. But the Landsat one, like I mentioned, goes back to 1984. So it's a much longer time series, and it's one that would overlap fully with all of the LTR data sets that started roughly in the year 2000. So I'll just work through this and can follow along. If anybody has questions, either here or on Zoom, just stop me in the process. This first part, you just need to do it once. It's to have a state boundary map for California. If you have a Mac, it's probably not going to work, so just ignore that part. Then there's just a few standard packages to load. The NCDF4 is related to the data type that the kelp canopy dataset is stored in. So you can download the dataset from the link that's here in the script. I've already done it just because it's a huge file and it takes a few minutes to download. It's a NC or netcdf file. So we use this function here, NC open, to bring it into R. The reason it's this file type as opposed to a CSV is just because it's more of a multi-dimensional data set. So it has spatial variables, time, biomass, like a bunch of things compared to like a CSV that's better at managing kind of two-dimensional data. So once we have the canopy file imported, I just am naming and extracting the variables of interest here. So year and quarter, self-explanatory. Then the coordinates for each pixel are the lat and long values. And then there's a biomass and standard error estimate for the biomass for each of those pixels. And what the biomass is referring to is an estimate of the wet kilograms of kelp at the surface. So all of the relationships between kelp canopy biomass were derived from diver data compared with satellite data initially to kind of build up the relationship between the two. So then I'm just making a separate data frame of time, and it can make it easier. I'll talk about it at the end, but for kind of manipulating the data by year or by quarter, it's nice to have a separate data file of time that you can use. So the next part that I have here, I just have it commented out because I typically keep the same structure for every project, but the location changes. So what I do here is just take a few minutes to figure out the bounding box for the area that you're interested in. So the data set that we downloaded is for the entire state, but you're probably only interested in like SBC reefs, a specific reef, specific region, or an island. So whatever your area of interest is in, you want to just like, you can do this in Google Maps, pull up the location, and you just want to find your east and west limit longitude, north and south limit latitude. So for LTR sites, it's really simple because we're basically on a north-south facing coastline. So for the example today, I just selected a small bounding box around Mohawk Reef. Yeah.
Can you do multiple boundaries for your one code? Like you can do Mohawk, you can do Naples, you can do.
Yeah, you can. I guess there are probably a couple of different ways to do that. It might be easier just to subset each reef separately and then combine them later. Because it's a lot harder to subtract areas out than to add them together. Yeah, so if you identify your bounding box, then you can just use this code here to subset the data frame again by that bounding box. I included this line here, which is a filter for NA data. So this again is part of the data checking process you have to do with this. Occasionally you'll get an entire data column that will be NAs. So it's common in like the first year of the data set, 1984. 2 of the quarters are just NAs, so there are no data. So you just have to decide at what point you want to filter out that type of data. But you can also have NA data for certain pixels within the time series, which is less likely, but it's just something to be aware of because you can run into issues doing data manipulation later. So that set builds your data set of kelp canopy data for Mohawk Reef. So you have the first two columns are the pixel coordinates, and then across each row is your biomass value for each of the quarterly time points. And you can see here, for example, the first and the third biomass column are just NAs. So those would be, I typically just remove 1984 and just start with 1985 because it's easier and more complete. Right, so then what we want to do is check the location of the data. So first, just to make sure that we subset it correctly, we need to know where those coordinates are. For this one, we're removing the NAs here just because it's easier just to remove all the NAs and plot the data real quick to see what you have. So we're just making a new data frame without any NA values, and then just setting up. There are a lot of mapping options in R. This one that I'm showing here is just a really basic one to just put a line in for the coast at roughly the same coordinates that you used above. You can make the area a little bit bigger just to capture some of the coastline so you know like what you're looking at. I kept it small here because I know where I'm looking. So this is just a little stretch of Santa Barbara coastline. And then the next step is plotting your points. So then you can see, if I make this a little bit bigger, you can see each pixel shows up on there, and then it's in the right location and shape for like what we know is Mohawk Reef. And again, there are other ways to test that using different mapping approaches, or you can use this same one and just zoom out further. And if you zoom out further, you'll see the islands and other kind of things you can use to orient yourself where the data is. So then if we want to actually display the data in some way other than just its physical location, one quick example here is just calculating average pixel biomass across the entire time series. So that's just doing a row mean for each of those coordinates. It's not taking into account any seasonality or anything. There are a ton of data manipulations that you could do at this point based on what your actual goal is, or if you need to subset it by like, if you're only interested in 2015, you can subset it for that year and do the same thing. But we're just going to look at average biomass across the whole time series. And then what we can do is plot that using kind of a nicer approach for mapping in R. So this is through the SF package. And what we need to do is just make sure that we have the correct spatial data assigned to this data set. So letting it know what the latitude and longitude are. And then the CRS code is just a code that's based on the projection of the data that you're mapping. So it's specific for the data set. This is the one, this is appropriate for here. And then these two lines, state names and this US states, is again probably not going to, this is where it's going to mess up for people with Macs, but it's not necessary. You can find alternatives to that particular package. And then this lets us, I might need to share a different screen for the people on Zoom so they can see this. Yeah. So this is, again, it lets us check that we're in the right location along the coastline, but we can do things like scale the color value of the pixels to the canopy biomass. So this is just putting the data on a simple color gradient with higher kelp biomass values in red and light values in green. So you can imagine that in the central portion of Mohawk Reef, this is telling you that we more consistently have high biomass. And then on the fringes, those are likely areas that are very intermittent with kelp, whether it's there or not, or if it has it, it's likely lower biomass values. So let me switch back to R. Yeah, so that's, again, it's just a way I like to do those kind of plots because you can visualize the data using color gradients. It's really helpful for presentations and stuff like that. Now, the last two lines here, I'm not going to go through these, but you can just, I'm like probably pretty bad example of how to like appropriately manage data. So I do stuff, sometimes I just download stuff and do it in Excel because it's easier. This is one of those cases. Lee's gonna hate me for saying this. If you just download both of these files, the canopy one that we set up originally and that time one that we set up at the beginning, you can just paste in time as two rows across the top, and then that gives you your year and quarter for the data set, and then it's easier to kind of pick the time frame that you want to work with. And then you can just bring it back into R afterwards. Or if you're better at R than me, you can just do it in R appropriately. Yeah, so that's basically it. If anybody has any questions about it, I can answer them now, or you can email me about it. But the main thing, I guess the main takeaway point is that although the kelp canopy dataset is a weird file type that you've probably never worked with, it's actually really simple to use and manipulate for like whatever your end goal is. So don't let the kind of structure of it be deterring in the beginning. Anybody have any questions? Cool. Switch over to Lee.
Okay.
So, but thank you.
Okay, thank you. Connected. Now we're gonna switch to our second speaker, Anne, and we're gonna talk about it's in a CSV version of the file, one of the SBC long-term research, and she will show you how she inspect the data set, and there's a potential, she help us find a lot of potential issues. So her trick was definitely useful for you to explore your data sets. Let's see. Switch to. Which window? This doesn't look right, is it? Is that correct?
That should be fine. Let me,
No, the screen window look like it focus on this. That's, oh,
it's there.
okay.
So everyone on Zoom, can you hear me okay? Just like some reactions. And can you see a screen that says SBC LTR data workshop? Cool, sick. Okay. Great. Well, thanks everyone for being here. I'm really excited to do this part of the workshop. Basically the motivation for me writing this is that I work with a lot of the SBC's like biological data. So as we all know, the SBC and other LTRs collect like annual survey data on basically all things kelp forest, and that's the data that I work with for my research. But I found that when I was downloading and using all of these data sets, they are essentially in the same format, and I do the same things every time, like cleaning the data, visualizing the data in some way. So that's what I'm sharing with you now, like basically the steps that I take every time that I download a new data set, clean the data and visualize the data. And so hopefully some of this will be somewhat new, maybe it'll be review, but essentially we're just going to use some common functions to clean and manipulate data and then visualize data. And at the end, we're going to come up with a time series figure. So it's time on the x-axis, and on the y-axis, we're going to visualize biomass. of red and purple urchins at Naples Reef. So at the end, we're gonna have this figure and we can say something about some dynamics of these two species at Naples. So that is what we're gonna do. So the first thing that I will say is that if you want to follow along, the link that is on the SBC website leads to this. So this is a rendered Quarto document. It's code with its output here. So you can sort of scroll through and follow along. But if you'd like to live code with me, that is also an option. And so I'll be working in R here, and I'll be working off of this this Quarto document here. And I sent this out in an email. Hopefully you all got that, and if not, I'm super happy to share this with you afterwards as well. So again, a couple ways to follow along if you'd like. Also, if you haven't used Quarto, I really recommend it. It's really similar to our Markdown. If you've used Markdown documents, but Quarto has this sort of like additional functionality, and I think it's more aesthetically pleasing than an R Markdown. So that's what I'm using here, but it allows you to combine code and commentary and all of these things so that you can sort of provide context for the code that you're writing. So I'll be working off a Quarto document. So in this section of the workshop, we're going to be working with the seasonal time series data. And this is data that's collected 4 times a year. Yeah. Yes. Seasonal data. Yeah, 4 times a year at 5 sites. Yes. In the SVC, and this is the full citation for this data set. And that's what we're going to be using. And so the first thing that we're going to do is just a setup. So we're going to load in this package called the tidyverse. And the tidyverse is basically a package of packages, and it contains a lot of functions that I use for cleaning up data, and I really like it, so we're going to load that in. If you're running R code, again, just as a review, you can hit Command Return, or you can hit this sort of green play button here, run current chunk, and that'll just run that chunk of code for you. So we're reading in the tidyverse, and now we have all of our functions in R to use. We're also going to use this package called Janitor, and Janitor is another super useful package with a bunch of functions to help you clean your data. So we'll load that in as well. Okay, so now we have our packages loaded in, and then we are going to move on to the next section, getting data from EDI. And so this code I didn't actually write, but I got it from the Environmental Data Initiative. So every data set on EDI has this section called like code, like analyze the data with some coding language, Python, R, C++, whatever. And so I just copy pasted this from that section into this script. And it works now, but as Lee has helpfully reminded me, EDI is about to change the way that people access the data on the database. So you will soon have to sort of authenticate, log in to download data. So for now, as of like the 20th of February, 2025, this works, but it might change in the future. So the first thing that we're really doing is just getting the URL, and this again is the URL for the data. If you copy pasted it in Chrome or Safari, it would lead you to the data. The next thing we'll do is basically create a temporary file using this temp file function, and then we'll download the data set into the temporary file. And after downloading the data set, we'll read it in using this function read.csv. And that is it. So again, I didn't write this code. I just copy pasted it from EDI. So I'm just going to run that code with this green chunk here. It's going to take a little bit, and you do have to be connected to the wireless for this to work. So it's going to download the data. And then the way that you know that it worked is if you look at your environment tab in RStudio, you will see this object called DT1. It's just data table 1. Okay. I don't want this to be up on the screen anymore. Okay. So we've downloaded the data, but the first thing to do when you are working with data is to look at it. So we know that it's there in our studio somewhere, but we really should look at it. And I think that this is like an underappreciated but really crucial step, to just like look at your data when you first read it in. And if you do that, you're gonna build like an intuition for what is in the rows, what's in the columns, and then you'll be able to work with it further. So one way to really quickly look at the data is to use what's called the glimpse function, which is from the tidyverse. So what I'm going to do is write in glimpse parentheses. So I'm going to open up those parentheses to tell R that I want to use this package or this function, and then I'm going to put in DT1, just the name of the object in there. And then when I run that line of code, what I will see is this basically summary of what's in that DT1 object, what's in the data. So what we see is we have 84,316 observations. Okay, so that is 84,316 observations of lots of different species at lots of different sites at many different time points. And we also have 24 columns. And it lists all of the columns that are actually in this data set. So for example, we know that there's a column for year, and this data set starts in 2008. So that's the number that it starts with. We know that, for example, there's a column called scientific name, and that's the scientific name of whatever species is being observed in that particular row. So again, if we look at the data frame with glimpse, we can get a sense of what's in the rows and what's in the columns. But you can also just look at the object. If you click on the DT1 object in the environment tab, that'll open up in another tab, and it just looks like this. So it'll look like something that you could see if you open this up in Excel. So, okay. So we know what the rows and columns are. And again, the goal at the end of this section is to create this time series with time on the x-axis, biomass on the y-axis of red and purple urchins. So let's take a moment and think a little bit. I'm going to make you talk to your neighbor. So you have to do it. So if we are interested in the biomass of red and purple urchins at Naples through time from, let's say, 2014 to 2024, which columns would actually be most useful? There's 24 columns in this data set. You don't need all 24. So which columns would actually be most useful to you if that's a bigger chunk? So take a moment to talk to your neighbor. Oh yeah.
Same here.
Quarto is a thing. I love Quarto.
Living in the dark ages.
Quarto evangelist.
Yeah.
Okay. Ready to come back, maybe? Yes? Okay, so again, we're trying to make this time series figure, time on the x-axis, biomass on the y-axis, we're showing red and purple urchins. So which columns would be most relevant to you out of all 24 of these things? There's no real right answer, but there are lots of different columns. But which columns do you think? Year, yes. Year, probably. Scientific name. Yeah, there it goes. So year because we're plotting time on the x-axis, scientific name because we're dealing with species. Site, yeah. Site because we're interested in Naples Reef. So we're gonna need to choose observations based on the site. What's our y-axis? Biomass? Yeah. So the biomass column is absolutely relevant to us too. And in this case, we're gonna do dry mass. I think that's what it's called. Let me see. Dry underscore GM2. So I'm just plotting dry mass, but biomass, again, a column. If it's going to be our y-axis, we're interested in that column too. There's also like date. So in addition to the year, there's also a column with the actual date. So the year could be 2008, but the date would be 2008, February 28th or something. So yeah, so just again, by looking at the data set and thinking about what columns we need to create the figure that we want to create, that allows us to sort of select the things that we actually want and leave everything else. Okay, so now that we've sort of built our intuition for what is in the rows, what the columns are, now we're going to clean up the data. So let's just review. Remember that this data set looks like this. So each row is an observation, each column is some data associated with the observation, but we don't want all of that. So in this section, what we're going to do is we're going to filter the data set. We're going to clean it up a little bit so that it's easier to use. And remember that we're interested in purple and red urchins at Naples. So we're going to filter the data set to only include those species and that site. And then we're going to do a little bit more cleaning to make the data set easier to use. So in this section, I'm going to sort of live code this. So you're super welcome to follow along. But again, if you just want to, see the code wash over you, you can follow along the Clorter document as well. Okay, so here we're going to create this new object called urchins. Just going to create this new object called urchins and then use the left-hand assignment operator, so the left arrow and the dash, to start first with this object called DT1. So basically what I'm telling R is like, okay, create this new object called urchins, start with DT1. And so I'm just going to run that line of code. And then what pops up in my environment is this object called urchins, and it looks exactly the same as DT1. And that's what I would expect because I've just read in the old data frame. So now that I've done that, I'm going to use one of my favorite operators, which is the pipe operator. And the pipe operator basically allows you to string a bunch of functions together. So you don't have to create a bunch of intermediate objects in R to get to the last thing that you want. We're just going to use the pipe to string 1, 2, 3, 4, 5, 6, 7 functions all together to get to a final data frame. So the way that I will do that is hit Command Shift M, and that gives you the pipe operator in the McGritter package, which is in the tidyverse. So what I'm telling R is, again, create a new object called urchins, start with DT1, and then I want to use a function from janitor to make the column names lowercase. And the function is clean underscore names. So again, we're creating this new object called urchins. We're starting with DT1, and then we're using the function clean names to clean up those names. So if we look back at this urchin's object, now all the columns are in lowercase instead of in all caps. That is a nice little touch for me because I am not an all caps girly, okay? So like I prefer when the columns are in lowercase because it's just easier for me to work with the data that way. So we have used this function from janitor to make the columns names lowercase. But the next thing that we want to do is actually select the columns that we want to work with and then leave all of the rest of them that we don't want. So again, I'll pipe in Command-Shift-M, another function called select. And select is from dplyr in the tidyverse. Again, the tidyverse being a package of packages, you don't have to load in all of these individual packages. You only have to load in the tidyverse and that's it. So if I'm selecting the columns of interest in this example, I'm going to use year, comma, date, comma, site, comma, dry underscore GM squared, comma. And then in this case, I'm not going to use scientific name because when I was writing this workshop, I forgot the scientific name of urchins. So I'm going to use common name because that's what I remembered. So again, we are creating this new object called urchins, starting with GT1, using clean names to make all the column names lowercase, and then we're selecting these columns that we want. So in this case, we're selecting year, date, site, dry, GM squared, which by the way, biomass is in dry grams per meter squared, and common name. So then if I run that line of code and then I look back at my urchins data frame, I see that I'm missing all of the other columns and I only have the columns that I want. Okay. So again, a little bit easier to work with the data with a smaller number of columns. And then I'm going to pipe in another function to make sure that the date column is read in as a date. And the reason you would want to do this is because even though this column looks like a date 2008-01-10, so the 10th of January in 2008, R reads that as a character string. So essentially it thinks that these are anything other than a date. So a bunch of integers and symbols, that's not actually a date. So what we want is for R to know that it is a date. So what I'm going to use is this function called mutate. Mutate is a really powerful function, again in dplyr in the tidyverse. It allows you to manipulate columns. So if you want to do something at the column level, you can use mutate. And what I'm going to do is write in mutate date. So the column that I want to mutate, the column that I want to manipulate is date. And what I'm going to read in, or what I'm going to type in, is say that date equals as dot capital D date. So basically what I'm telling R is take this column date and transform it into an actual date using the function as dot. So if I run that line of code and I look at the object, it doesn't look any different. The date column doesn't look any different. But if I try glimpse urchins and run that, now I will see that this column of date, before it was a character, now it is a date. So now R knows for sure that this column includes dates. Okay. But we have a bunch of other functions to go through. So we're going to pipe in a new function. And we're going to make the site and common name lowercase. And again, I do this because I want everything to be in lowercase. I find it easier to type in. So we're going to use another mutate, except it's actually going to be mutate underscore at. So if you want to mutate across many columns, you can use mutate underscore at. And what we're going to do is open up C for the first argument. So the C parentheses indicates to R that we want a list of things to work with, and the things in this case are the columns. So we'll put in C quotations site for the column site, and C quotations common name for the common name column. And then I'll use this function in stringer in the tidyverse str2 lower. And str2 lower converts a string to lowercase. So again, mutate at to mutate across multiple columns, site and common name, using the function str to lower. And then when I run that line of code and I look back at urchins, now I see that the site is in lowercase, as is the common. So again, a little bit easier for me to work through the data that way. Okay. And now we're going to start filtering. So remember that this data set includes how many observations? 84,316. We don't want all of those. We only want the ones that we're interested in. So I'm going to pipe in another function, Command Shift M, and I will filter. So the function filter is in the dplyr package, again in the tidyverse. Filter allows you to work at the row level. So we're filtering observations between 2014 and 2024. And the function that we'll use is between. So within filter, there's another function between year, and that's our year column. The second argument is the beginning of the range, and the third argument is the end. So again, what we're using is filter to filter the observations in the data set. We're using the year column to specify that we only want observations from 2014 to 2024. Now, if we run that, look back at urchins, we see, first of all, that there are fewer entries. So we know that that filter worked. We know that when we filtered for observations between 2024 to 2014 to 2024, that worked because we just have fewer observations. But you can also just look at your data set. And you can see before, just remember, before it started with 2008, now it starts with 2014. So you know that that step works. So there are two pieces of evidence to suggest to you that that code actually worked. So now we've filtered, but we are, again, only interested in red and purple urchins. So I'm going to pipe in, again, Command Shift M. And we're going to filter again to only include red and purple urchins. So we'll filter. And now the common name is the column that we're working with, common name. And we're going to use this operator because we want to filter for two different species. We're going to use this operator called the in operator. And that's %, in %. What you're telling R is that you want to filter, but you're telling R to look for objects in a list. So because you want to filter for more than one thing, you're going to provide a list. And the list, similarly to what you use in at, is going to start with C. And then in that, you're just going to type in the common names of the species that you want. So in this case, it'll be red urchin in quotation marks, and then purple urchin in quotation marks. So again, we're filtering to only include red and purple urchins. And now if I run that code and I look back, now we can see this is closer to what we're looking for. So all of the other species are cut out. We're only looking at purple and red urchins. Okay. And then the last thing is that we were only interested in Naples Reef, but this still has all of the other sites. So now we're going to do our last filtering step. So again, piping in Command Shift M. We're going to filter to only include Naples. So filter again, site. And now, since we're only filtering for one thing, we're only looking for one site in Naples, we'll hit the double equal sign. So what that's telling R is to provide a direct match in the site column. So for every observation in the site column that directly matches what I'm about to type in, which is just Naples, lowercase, that's a direct match. Filter the whole data set. And that's in quotes. So now if I run that line of code again, now it says that it's empty, Y, NAPL, perfect. Thank you, okay. So that's a really good example of how this works, right? So you have to exactly provide what is actually in that column. And if not, R is not going to like assume that you meant an APL when you wrote it. This is like, I think the sort of thing that I think about quite a bit. So R is super powerful, but in exchange, it requires precision in what you provided. Okay, so now if we look back at urchins, we see that we have all these observations of red and purple urchins. They're only from Naples. It's only from 2014 to 2024. And now we are ready for the next step, which is my favorite step of any research project, visualizing the data. I love visualizing data so much. It is the only thing that I want to do all day, every day. So if you are ever like interested in visualizing data and you just like want to like bounce ideas off someone, please talk to me. I love talking about figures. And there's also so much out there in like the R universe of people who think really deeply about data visualization. And I'm super happy to share those resources with you. So anyway, this whole section could have been like paragraphs long of like my thoughts on data visualization, but first step I think is to read this book, the ggplot user manual. So the functions, the package that we're going to use to visualize the data is ggplot2. It's the tidyverse. It's my favorite package to visualize data, and this is like a really comprehensive guide for how to use that package. So the way that ggplot works is that it has three basic parts. We're going to walk through those parts in code. The first part is the global call. So basically you're telling R that you want to use ggplot. You're just saying, hey, R, please use ggplot. So that's the global call. The second part are the aesthetics. And the aesthetics basically outline the x-axis, the y-axis, the colors, the shapes, whatever it is that you want to actually visualize. That's in the aesthetics. And then the third part are the geometries. So these define like shapes, lines that you want to draw. And these functions all start with geom. So if you were to type in geom underscore something and ggplot was loaded, you would see all of these options for geometries. So you can make a box plot. You can make a density plot. You could make a function. You could make a histogram. So there are so many different types of figures that you can make. And they all come from the geom underscore function. And then if you wanted to make your visualization like a little bit more beautiful, you could adjust colors, you could adjust look, you could adjust labels. Again, there's so much more than just these options, but I'm just going to present to you some basic ones. So, okay, so all of this code is written out. I'm just going to comment out what it is that I'm actually doing in the code. So the first thing is this global call. So here we open up ggplot function data equals urchins. What we're doing here is specifying the data set or the data frame that you're using. We're saying data equals urchins, and again, that's the global call. So you start with ggplot. You saw this in Kyle's section too. He made a plot in ggplot and he started with ggplot. The next part is the aesthetics. So here we're going to specify what the x-axis is, AES, open parentheses, x equals date, y equals dry underscore GM, and that's again the y-axis. And in this case, because I'm plotting the time series for two different figures or two different species, I want them to be different colors and shapes just to be able to see on the figure what is going on. So I'm specifying color, so that'll be the color of the points. And shape, so that's the shape of the points. So if I just like highlight this, just the global call, so from in my code line 166 to 172 without that plus sign and run it, nothing shows up. And that's because I haven't specified my geometry yet. So again, those three basic components of a ggplot function includes the global call, includes the aesthetics, but you have to have geometries for some plot to show up. So we're going to start with geom underscore point to just make some points. So now if I run this again, I'm highlighting from 166 to 176 without that plus sign and running it. Now what I should see is something like this. So again, on the x-axis, we have our date, time. On the y-axis, we have dry biomass. And then the points represent the dry biomass of purple urchins in red circles or red urchins in blue triangles through time at Naples. We have successfully created a figure, but it can also be more beautiful. So because it's a time series, I typically like to draw lines connecting these points. So I'm going to do that using the geom line function. So again, I'm going to run lines 166 to 178 without that additional plus sign. And now what we see is lines connecting those points. So again, it's a little bit easier to see. We see the red urchin dry biomass is super high early on in the time series, but then declines, and then purple urchin biomass is generally lower relative to red urchin biomass. So, okay, this is like super basic, right? So this is the most basic formatting for a ggplot plot, but we can change the colors to be more intuitive to us. So red and purple urchins, as common names, have colors in them. So we can specify colors. So we can change the colors of the points using the function scale color manual, and you're just adding on another layer to your original ggplot. So if we run that, all of a sudden we get red and purple points for red urchins and purple urchins. We can also use a theme underscore minimal to just change the theme. And so the default ggplot theme has this gray background, white lines, which to me is not potentially the most beautiful. But if we use theme minimal, what that gives us is a cleaner background. So it's white with light gray lines. It's a little bit cleaner. It's harder to see on the screen, but if you're running it on your computer, you can see the gray lines too. And the last thing we're going to change are the labels. And so this is like underscore date, dry underscore GM2, common underscore name. And that's just like visually not especially aesthetically pleasing. So we can change the labels using labs. And this takes specifications for all of the labels that you might want to change. So on the x-axis, I'm going to change date to capital D date. On the y-axis, I'm going to change dry underscore GM2 to dry biomass, and in parentheses, cite the units. And then I'll change the title of the legend to be species, and then I'll just create a title for the whole plot. So now if we run this whole chunk of code, now what we see is something like this, like a clean plot with date on the x-axis, dry biomass on the y-axis, species, and a title for the actual plot. And that's it. That's your time series plot. And I make these plots a lot just so that I can get a sense of the dynamics of these species through time. And it's really useful for me to understand what these species are doing so that I can actually put my research questions into some biological context. And also, this is a great plot to make if you are trying to make sure that all of the data actually makes sense. So this is a real example from my own research, but I was working with the kelp removal data set, and there was one biomass point that was like super high for whatever reason. And I made the visualization, I talked to Lee about it, and then Lee discovered that was actually just an error in the way the data were entered. So we were able to find that error essentially by making these time series plots, and we were able to fix it and make sure the data was right. So it's useful to just make these plots before you get into any analysis, just to get a sense of what is happening in the data set and see what's going on. And that is it. So again, if you want to ever talk about data visualization, super happy to do it. And I will take questions at this point. Before moving on this week. Yeah. Yes, actually, yeah, for sure. I discovered this really recently, but you can actually use Unicode to do it. So if you do like \U, I think 00, I want to say it's B2. Yes. Yes. So you can use Unicode for superscripts, subscripts, symbols, whatever. Yeah. I saw it. Okay, cool. All right. Oh, okay.
Oh,
Got it.
congratulations.
Thank you. Thank you. Okay, cool.
Okay. Thank you for our speakers, and that's a wonderful experience that they have when they deal with their data analysis. So thank you for sharing their experience. I just say that I'm a super coder, but today I'm gonna show you something about non-coding. The reason I want to do that because over the past years, when I keep telling people, oh, hi, let's start doing coding. Everything need to reproducible. So we need to code. Everything should be documented in the code, including comments and how you deal with the data in every step. But I have to admit that many of us just not a coder. And so they keep running into the issue of, okay, how do I read this data? This data is so big. And how do I deal with it? I don't want to subset the data set. I only want one site. And so we don't want to stop students from research their data set if they're really not a coder. So, and when the ChatGPT comes out, I was like, this is a great tool. So that's why today I stand here and let you share some experience about this specific tool for you to do your data analysis and data inspection without having to code. Okay, so couple things. The ChatGPT I use is a paid version of it. So for some of you that don't have the paid version, you're probably not able to repeat the steps that I'm going to do. But if you decide to go into a paid version, this is what you're going to get with a $20 monthly fee. I have to say that I am a coder. So for anything that you want to reproduce, after you do this first inspection, you still have to translate into the code. So you are able to reproduce next time if you want to see the same figure. So let's go with that. So turn that off. So this is, let's see, are we going this for the, are you guys able to see the ChatGPT interface for the online speakers, for the online participants? Okay, great. So this is a ChatGPT interface. For the paid version, you have on the left-hand side, you can explore the GPTs, which means it's a lot of GPT tools that are created by the other people to make your life easier. For the non-paid version, I believe there's no option for choosing this part. So if you choose that part, you were able to get on a search window. Like you can search a lot of ChatGPT tools. And if you want to do the image generator, if you want to do the writing, if you want to do search for the scholars, literature review, there's a lot of tools that you can use. But today I want to focus on the data analysis. So I always like to type in, if I want any tool, I just type search the tool, and typically I go with this first one. But because they typically list the ones that most of people use, and which also means ChatGPT is a large language model. It's get trained a lot because a lot of people use it. So it can be slightly more sophisticated than the tool that maybe only 10 or 20 of us use. So I go with the first one, and I already have it here on the side window. And so we can start explore this data analysis tool that have been already be trained by 600,000 people online. So here's what I do. Assuming that we're getting a data set from someone. So today I use this data set. I don't even have to tell you what that is. You will see and say running through it. So it's just a data set in the CSV file. I drop into this window. And then let's start from there. So I drop this CSV file in the ChatGPT, and then click, and then tell it, say, tell me something about this data table. So it starts running an analysis on this data table in a way that hundreds of people that have been trying. So it will tell you something. Okay, first, it give you some first few columns, first few rows, and then you can scroll over and then see what they are. And there, okay, you can have a glance of, this is a data set with many scientific names, groups, surveys, and as mostly focused on the fish. And I can tell you a little bit background. This is one of our annual survey. So I asked you to tell me something about this data table. It actually, in the background, it runs through the Python, and then runs through a whole bunch of checks. You don't even have to see that because I want to see the summary of his. So it gives you some key perspective of the data, including years, months, date, survey locations, which including site, visibility. It can even tell you, just from the column name, VIS, it can even tell you this is visibility of your survey. And there's a transit, there's a species code, scientific name, and it can already do the interpretation of what that column name actually mean for you. So, and then it tell you that there's a taxon, kingdoms, genus, and including it can even tell you that's a fish size. Look at the size definition, the fish size. I never even tell this ChatGPT it's a fish data set. It tells you this is a fish size. And then the count, the number of individual recorded. So it interprets the column name. And then also looking at the data, has a whole bunch of scientific name. So you do its interpretation and tell you what he think this data set is. And also survey area. And some other information, including notes, groups, surveys, mobility, and growth morphology. And it even tell you initial observation of the data. And then it tell you there's 8,400 missing. So if I'm a data manager, when I saw this data set, why is missing? I may keep looking into it, why is missing? And then I look at it, there's a negative value for the size column, -99. Oh, because we didn't tell the ChatGPT that -99 is in there, which is actually is a missing value, and there shouldn't be a negative value. So the next step I'm gonna do is -99999 is missing value. So I had to tell him. So it knows that. Got it, he said got it. He cleaned it, and then now he knows, oh, it's a missing value. And then so it redo its analysis and tell you something about the data set. So the size column still have that many missing values, and it switch over. So when I look at this, I tried this on a few other data sets. Say, oh, okay, so it gave me some summary of what I need to pay attention to if I look at this data set. without scroll down the CSV with thousand rows. So it gives you some sense, a quick scan sense of what that is. And then it asks you, here are some possible next steps. Do you want to do the fish count analysis? You want a size distribution if you're interested in particular fish size? Do you want to do some biodiversity analysis? You can do all this. And I try out some other data set. You can do all this. But before that, because my purpose is doing data inspection on the data. So I want to know, before I run into any analysis, I want to know some other tricks on this data set, some other things that I'm not aware of. So I was like, okay, so what do I want to do? Okay, give me some summary of the numerical, the minimum and maximum. I want to know that if the numerical column is actually in the right range, because I may suspect someone accidentally put in 100 for a species can only show up one time in the survey. So I want to do some inspection on that. So for numerical column, for the size 1 and 220, understandable. We're gonna have some shark or something as big as 220 centimeters. For the count, -99 for sure, that's NA value. But we're gonna have some fish that are up to 100. And that's also reasonable for some schooling fish. So it's not too out of my expectation. Okay, let's see. What about if I want, let's do something ended. I want to see the fish at navel. Plot the time series figure for all species. It's doing this Python code behind the thing. So it makes sure it doesn't tell me something that's he make it up. All right, so this is time series figure of all the species are there. Okay. What is that? I curious that the top one. What is the top abundant species and this figure? Because there's so many lines, so I'm not able to see from the legend that what that is. I just ask it. Okay, is this a species? Okay, I'm curious to, how about we'll have a zoom in of this species? Okay, let's look at the snorita for time series figure across all sites, because I want to see how this species doing, including in all the other sites. Okay. It's doing its work. That's crazy because it didn't deal with -9999. All right, let me tell you. -99999. I believe that maybe have in the count to be treated as NA. So this is a communication that's necessary when you're doing data analysis on the ChatGPT. You have to really treat it like a human doesn't know anything, and then you have to communicate with it with your specific requirement. Okay, you plot that way. Okay, so it show me, in fact, ABUR looks like, oh, Napo looks like it's the highest. So this species only abundant at Napo, and it's crazy abundant at Napo. So from this figure, oh, this is the case. Okay. How about, let's see. Could you subset the data to Naples and generate the subset Naples to Naples? Okay, I'm just gonna do that one, see if. Okay, and now I want to show you is, it asked me, analyze the train for specific species at Naples. Yes, one. I choose one because I want to know the train line, if that fish actually goes up or goes down. So many species. How about kelp bass? Choose only the kelp bass. I just type in a kelp bass. It doesn't really match the actual common name in the data set. So it has to do its own search and to make sure they match the actual names in the data sets and also do the filtering. Okay, this is a kelp bass. Oh, okay. Look like it's increasing. How about put a linear regression line and tell me if the slope is significant. This is a data exploration, data inspection, and then you want to just know some stories before you really get in hard code in R or Python. Okay, so we put in the regression line, and then p-value is 0.0. Yes, it's well below 0.05, so it's the slope is significant. So you know kelp bass has been increased at a Naples site. So that's to give you a sense as you run through the ChatGPT. You have some sense of the data before you start hard coding. The great benefit of this I experience is then when you do some synthesis analysis, you need to look into hundreds of data sets, but you're not sure any of the data set actually useful for your analysis. So you go through this first glance of the data before you even do your hard coding. And it gives you a sense, oh, this data set is super useful for me. So I'm going to use that one. And if this is a figure that you're going to publish on your paper, and you want to reproduce this figure because you can't just really copy and download, you may not confident about just download this from the ChatGPT because this ChatGPT has been constantly trained. There's a possibility a month or two later, when you come back, you do the same thing. There may be slightly different on your figure. So in order to prevent that happen, you say, okay, give me the article that produced this figure. So get an R script, put it on your computer, and then you reproduce this figure for your future, or even modify some of them for your publication on the paper. Okay, so this is the R script. You can just copy and paste into a computer in order to reproduce this in the future. So, and then one more thing I was thinking to show you guys is I'll change the data set from the long format to the wide format. A lot of us, like even the R coders, have a headache about doing that. And so I was trying, it was like, okay, I want to subset the data to Naples only and convert the format to wide format, convert to the right format. To wide format using SP code because that's the common name. because when you convert from the long format to wide format, you can use scientific name, or you can use SB code, or you can use other thing. I just more specific tell it, this is the column name I wanted. Okay, and then it start doing its work. And then it converted, okay, into the wide format. This is already converted, so the species become a column name. And then for this case, you can expect because because if it's a data set that hasn't been quality checked, this data set is very good already, but some of data set hasn't been quality checked, you will see that some of those are not zero, maybe missing. So that's the time you need to go back and then check, oh, this is actually zero, or is actually missing, or is actually something I forgot to put in there. So it's a part of the quality checking process too. And so in order to preserve this, how about I say, I want to download it. Just tell it I want to download this in CSV. So it generate a CSV file. And here, it's only the enable wide format, and I can download it on my computer. Then I can pull out my survey sheet and check some of the records. So in this case, the whole process for the people who's not super coder, it's an easy process. You don't have to go on the Google search, what exactly that wide and long format transfer actually is. So this will help you to hopefully get your work more efficiently and save your time. All right, so that's just some of the data analysis tricks that I want to show you guys. And there's a lot more other things those kind of ChatGPT can do. As I say, this is the paid version of it. If you like to upgrade, this is what you saw. If you don't upgrade, I don't think you can dump the CSV file in here. You can only copy and paste from Excel and paste into the window. So not dumping the whole CSV file. So that will be the differences. Okay, so that's my talk. And today's talk is recorded. We will be posting on the website. And for anybody who's missing part of it, welcome to check out the YouTube video as well. Okay, any questions? Okay, we are good. Well, out early. Thank you. Thank you for the online participate too. Thank you. Thank you for all the speakers.